Hello and welcome, my name is James Leach, and this video will explore the concept of mechanical equilibrium as it appears on the MCAT Chemical and Physical Foundations section. Much like the MCAT itself, in this video we'll be covering the use of free body diagrams, as well as both the concepts of translational and rotational equilibrium. Our goal then will be to use free body diagrams first to understand the equilibrium state, and then to use those diagrams to solve problems such as the one at the bottom of your screen. What we'll be discussing in this video falls under the term dynamics, or the study of forces and torques, which will be defined shortly. So, on the MCAT, when you are faced with dynamics problems, the first place your mind should go is to sketching out a free body diagram which keeps track of all the forces and/or torques acting on the system in question in order to develop a complete and accurate depiction of the scenario, which will lead to accurate calculations and correct answers. So let's work through this example of a soccer ball sitting on the ground. The first thing you should know, and it's an easy one to neglect, but will lead to wrong answers if you're not meticulous in your work, is the force of gravity. Anything on Earth experiences the Earth's gravitational pull, and this ball is no exception. As the ball is not crashing through the ground to the Earth's core, there is a normal force acting upwards. That's the case of a ball at rest. If someone were to kick that ball, there would be a force applied in the direction of the kick. This diagram would be complete in most MCAT problems, but for problems where you're asked to consider non-conservative forces, and you would be asked explicitly, we would also need to consider air resistance against the ball's motion and the force of friction. It cannot be stressed enough that these diagrams are an invaluable way of keeping track of dynamic systems, since oftentimes, without a diagram serving as the link to the physical world, some forces can easily be neglected and lead to wrong answers. So let's start using them to our advantage and see how they can net us some correct answers on the MCAT. Translational equilibrium is a specific dynamic state wherein the object is experiencing no net force whatsoever and therefore no acceleration. Let's return to that soccer ball. If it's sitting absolutely still and we apply all of those arrows to the free body diagram again, there are certain things we know to be true of this system. The force of gravity and normal force must be equal as the ball is accelerating neither up nor down. Likewise, if there is no kick, there is no air resistance or kinetic friction acting on the ball either, so it accelerates neither left nor right. This ball is in translational equilibrium as there is no net force acting on it, causing it to accelerate. If the ball is kicked and it accelerates to the right across your screen, there must be a net force acting in that direction, or the force of the kick is greater than the force of friction and air resistance, so the ball is no longer in equilibrium. Now let's say we tune into this situation and the ball is falling with constant velocity thanks to the force of air resistance equaling the force of gravity. What's the situation now? Well, if there is no net acceleration, and there isn't because it's moving with constant velocity, then there is no net force on the ball, which means it's in translational equilibrium. This is a very important note about a very common mistake. Translational equilibrium means that an object has constant speed and constant direction, not that it is sitting still. The good news about rotational equilibrium is that it's more or less exactly the same thing, just that we consider torque instead of force to be the deciding factor. Where force causes translational motion, torque is more properly responsible for rotational motion, though a force is still required, as we'll see. Torque is just force which causes rotation. It depends upon r, the moment arm or radius, which is simply how far away from the fulcrum rests the point at which force is applied. Seeing that torque is directly proportional to r, we can figure out which one of these equal force arrows would inspire the greatest torque. It has to be the blue one, as it is furthest from the fulcrum and has the greatest r value. Similarly, torque is proportional to the amount of force applied. If we apply two different forces at the point where the blue arrow lies, the greater force will cause greater torque. Lastly, torque also depends upon the angle at which the force is applied relative to the moment arm. The maximum absolute value of the sine function is 1, and the minimum value is 0. Thinking about which angles elicit these values, we can figure out which of these three arrows results in the greatest torque. Sine of 0 degrees is 0. Sine of 180 degrees is likewise 0. Halfway in between, we have 90 degrees, where sine reaches its maximum value of 1. So of these three equal forces, the one applied at 90 degrees elicits the greatest torque. which makes sense when we actually think of turning a wrench. We don't apply force at weird angles. We grasp the handle and form a right angle with our forearm and the wrench in order to be maximally efficient. So here, instead of equal forces causing translational equilibrium, equal and opposite torques cause rotational equilibrium. Those are the concepts. Now let's apply them to some critical thinking problems. Try this first one. Essentially, we need to spot a difference between these two runners, which would render one of them faster than the other. Thinking back to what was discussed in this video, we have to consider all of the forces acting on these two runners, the same forces that acted on the soccer ball, except subbing in the runner's own strength for the force of the kick. Generating upwards force won't make someone run forwards more quickly or slowly as long as they are generating the same amount of force in the forwards direction as the question stipulates. The same stipulation renders B wrong as well, since they both generate the same amount of force when running, regardless of who has stronger legs. If the runners have different body shapes, however, they will experience different levels of air resistance, meaning one of them will accelerate more quickly. C is a good explanation, while D again is irrelevant in this scenario. So C is our correct answer. Give question number 2 a shot. First things first, doors rotate when they open, so we're concerned with torque here rather than pure brute force. So let's call up that torque formula. Answer choice A, however, is somewhat concerned with force. Creating drag or a friction force which necessarily opposes movement in only one direction, the designer makes the door more difficult to open from the outside. If the surface on which a person can push is angled away from 90 degrees where torque is maximized, the door will again be harder to open from the outside. Moving the area where people push higher will have no discernible effect based on the information we're given. So C is our answer, as D successfully reduces the value of R and would be a viable solution. Try one last question on torque. Here, we're going to have to pull out that torque formula and get calculating. Subbing in the values from the question stem, we see that the torque resulting from force A is 0.9 Newton meters, while from force B we see 0.96 Newton meters in the clockwise direction. As such, the net torque is 0.06 Newton meters in the clockwise direction. In this video, the applicability of free body diagrams to all MCAT dynamics problems was explored. The state of translational equilibrium was defined as the dynamic state in which the sum of all forces on an object is 0, and the state of rotational equilibrium was defined as the dynamic state in which the sum of all torques on an object is 0. Understanding the equilibrium state is critical, since any object or material you'll see on the MCAT that is not accelerating is indeed in equilibrium, and you'll need to be prepared to recognize that. So good luck in doing so, and thanks for watching this video.